proving that e to the x is its own derivative is one of those classics. And if we are allowed to assume that we know the power series of e to the x, we're assuming that e to the x is equal to the sum from k is 0 to infinity of x to the k over k factorial, 1 plus x over 1 factorial, x squared over 2 factorial, x cubed over 3 factorial, so on and so forth. If we're allowed to assume this, there's a really easy way to prove this. And what we'll use is this property of convergent power series called term-by-term differentiation. Basically, what it says is that if you want to take the derivative of a power series, you can just do it term by term. Or put it another way, even though there's infinitely many things added up here, you can just bring this to the inside. And let's notice that k factorial is a constant with respect to x, so I don't have to worry about it being in the derivative. All I need to do is take the derivative of x to the k, and that gets me kx to the k minus 1. Awesome. Okay, well this certainly looks different, at least at first glance, but let's see if we can simplify things a little bit. All right, well, first things first, let's notice that we have this k here, and we're starting at k is equal to 0. That means the first thing that we would get is 0 plus a bunch of other stuff. I don't need to plug in a 0 to get a 0. That doesn't help me any, so I could just replace this with k is equal to 1 to infinity, because I'm just getting rid of a 0, which doesn't get rid of anything. Okay, well, what else can I do to make this look more like the original e to the x? Well, the next thing I can notice is that I can reindex. I could just take k is equal to 0, and what I'm doing here is I'm reducing the number I'm plugging in by 1, which means I need to add 1 to all my k's on the inside. And there's where we start to see things cancel. First of all, obviously, 1 minus 1 cancels. Here on the bottom, I could rewrite that as k factorial times k plus 1. K equals 0 to infinity, k plus 1, x to the now it's just k, and then those cancel. Finally, took us a while to get here, but we get that x to the k over k factorial series from k equals 0 to infinity, and gosh, that's e to the x. So that finishes my proof. The derivative of e to the x is in fact just e to the x. Okay, well, proving this with the series, the formulas for the terms of the series could be kind of tedious, so maybe you just are going to believe me if I just do it with the first few terms, and it's far easier just to see it here. If I take the derivative of e to the x, and instead I just think of it as the derivative of 1 plus x squared over 2 plus x cubed over 6. Well, what do I get? I get 0 plus 1 plus 2x over 2, 3x squared over 6. Get rid of that 1. That's 1 plus, cancel those, x plus, cancel those, x squared over 2, and that is 2 factorial. If you had more terms here, x to the 4th over 24 gets you 4x cubed over 24, gets you x cubed over 6. That's 3 factorial. You can kind of see how term by term it fits, but of course to handle all those infinite terms in a rigorous proof we had to use the kth term formula for each term of the series. Okay, let's do another example of applying term by term differentiation. We're going to find the Maclaurin series for this guy right here, and to do that we need to start with the fact that we know the Maclaurin series because we know some power series converging. There's a missing piece of this problem. We're assuming the domain is -1 to 1. I apologize for not having that as a part of the problem, because this Maclaurin series that we have for 1 over 1 minus x only works from -1 to 1, and it's simply x to the k. 1 plus x squared plus x cubed plus x to the 4th, so on and so forth. This works for values of x between -1 and +1. Okay, from the geometric series formula. Now, if I want the Maclaurin series for this, well, all I have to do is remember that, well, what is the derivative with respect to x of 1 over 1 minus x? That is, in fact, -1 over 1 minus x squared. Excuse me. That's enough mistakes.